Okay, so last class we talked about what transition metals are and some of their physical properties. Remember, transition metals form ions with partially filled d orbitals. And also remember that zinc is not considered a transition metal because it's d sublevel, so all of the d orbitals are completely full. When it loses 2 electrons, the 2 electrons that are lost are from the s orbital, so the entire d sublevel remains full. What we're going to look at now is we're going to take a look at some of the chemical properties of transition metals. The first thing that I want to talk about is the idea that transition metals have variable oxidation states. So that means for one specific element, say for example copper can have more than one charge and still be stable. So it can have a 1 plus charge, for example, but copper can also have a 2 plus charge. Okay, so that's what we mean when we're talking about variable oxidation states. The reason this happens is very particular to the valence electrons of transition metals. So the valence electrons of transition metals are all located in the 3d sublevel. And so the electrons have quite a similar amount of energy required to remove them. So it's just as easy to remove electrons in the 3d orbitals because they're all at the same level. What that means is that there is a similar ease, okay, in losing different amounts of electrons. Okay, so quite often that means that they have more than one charge. For example, losing 2 electrons or losing 3 electrons is just as easy, and so they have similar stability. So these ions are similarly stable. Okay, let's take a look at exactly what we mean. So if you take a look at this graph along the y-axis, I am charting the number of ions formed. So for example, scandium can form 2 stable or common ions. Titanium can form 3, etc., etc. Okay? And so hopefully you can see a pattern as we go from left to right across the periodic table. You should see that as we start from scandium and move on towards manganese, more different kinds of ions can be formed. And that's because as we go from left to right, there's more electrons of similar energy. So remember, each step to the right, we're adding 1 more electron. So this trend occurs because there's more electrons of similar stability. They are all located in the 3d sublevel. Okay? You'll also notice another trend as we continue onwards towards the right. Past manganese, you'll notice that our number of possible ions that are stable decreases. Okay? This is because of the idea that the protons in the nucleus of these elements are able to have a stronger attraction to the electrons. So there's a stronger attraction to the electrons because we have more protons as we step over to the right, and because of those more protons with the same number of shielding electrons, it becomes harder and harder to remove those electrons to create multiple different ions. Okay? One of the chemical properties of transition metals, to recap, is that there's variable oxidation states. They can have ions of different charges. Now, you do not need to memorize this graph below because all of the different stable ions of these transition metals can be found in your data booklet. Okay, now another chemical property of transition metals is that some of them tend to be magnetic, and the magnetism depends on the electrons in the d sublevel. So it depends on how they're arranged. So it depends on the d sublevel electrons. So these electrons can basically be arranged two ways. In one case, the d sublevel electrons can be all paired up. So in every single 3D orbital, all of my electrons can be paired. Alternatively, some of my electrons in the 3D sublevel might be unpaired. They might be by themselves in that specific orbital. This results in two different phenomena. So when we have all paired electrons, we have a substance that's known as diamagnetic. Diamagnetic. And what that really means in everyday language is non-magnetic. So it's not magnetic when all of the electrons are exposed to a magnetic field. There's actually a weak repulsion. So there's a weak repulsion when these diamagnetic particles are exposed to a magnetic field. An example of a diamagnetic substance might be something like zinc. So although zinc isn't a transition metal, it is an example of a diamagnetic substance. So if we think about zinc's d electrons, let's draw the 3D sublevel. So again, the 3D sublevel contains 5D orbitals. And in zinc specifically, all of my electrons are paired up. And so this material, zinc, is not magnetic. All of the electrons are paired. It's considered diamagnetic, and if exposed to a magnetic field, it will be repulsed. Alternatively, if we have some amount of unpaired electrons in the d sublevel, we have two different phenomena that take place. So we can either have a substance that is known as paramagnetic or a substance that's known as ferromagnetic. Now, let me just finish writing these and I'll explain the difference. So, a ferromagnetic substance and a paramagnetic substance, both of them are attracted to a magnetic field. To a magnetic field. So what happens is, if these substances come into contact with a magnetic field, all of the electrons' spins line up, resulting in an attraction that the material has to the magnetic field. Okay? However, ferromagnetic substances go one step further. Ferromagnetic substances retain their magnetic properties after they've been removed from the magnetic field. So they stay magnetic even though they're no longer in a magnetic field. Okay? Whereas paramagnetic substances lose any magnetic properties as soon as they're no longer exposed to a magnetic field. Now, the three examples of ferromagnetic substances that you need to know for IB chemistry: iron, cobalt, and nickel. Okay? Everything else that has unpaired electrons is considered paramagnetic, and some examples of these guys might be titanium, for example. Okay? So again, the substance's ability to be attracted to a magnetic field depends on d sublevel electrons. If the d sublevel electrons are all paired, so in each orbital there's 2 electrons, we consider the substance to be diamagnetic. It's not magnetic, and it actually shows a weak repulsion to a magnetic field. An example is zinc. When all of our electrons are paired, we can have 2 scenarios: paramagnetic and ferromagnetic. both of these cases are attracted to a magnetic field, but specifically ferromagnetic substances retain their magnetic properties. The three examples that you need to know of ferromagnetic atoms are iron, cobalt, and nickel.